same area, the number of cooling degree hours has increased by a factor of 33%. Yeah. But once, this is the impact of the global climate. But once we move inside the city, towards the western part of the city, where urban heat island and urban overheating is important. In this case, the number of urban, let's say, the number of cooling degree hours has increased by a factor of 81%. And if we move to the very western part of the city, where really overheating is very important, the number of cooling degree hours has increased by 300%. And these are real numbers. So you understand that the impact of regional climatic change is very important in our cities, much more important than the impact of the global climatic change. Is it just the impact of urban overheating on energy that really has to worry about it? No. The environmental impact of urban overheating is extremely important. We know very well that because of the high temperatures, we have photochemical reactions in the atmosphere, and this increases the concentration of the ground level ozone. Ground level ozone is a killer. And actually about, let's say, 87% of the episodes of high ozone level is because of the global and regional overheating. So the impact really of high temperatures on the environmental quality is extremely high. But it's not just that. We know very well that during the period of heat waves, or when temperature is increasing, the emission from power plants is increasing tremendously. Average statistics shows that about, let's say, the increase of the emissions by power plants because of the temperature increase is of the order of magnitude of 3%, per degree. So imagine during a heat wave that we may have 10 degrees of higher temperature, the increase of the emissions of SO2 or NOx or CO2 may be of the order of magnitude of 35%. This is really very important. At the same time, as I have already mentioned you, urban overheating has a very serious impact on the peak electricity demand. If really you try to see and examine the number of, let's say, electrical grid failures recently in the United States between, let's say, 2015 to 2021, you will see that there is a tremendous increase during the very last years that affect very much the efficiency of the power plants and affects also the cost because it asks for additional, let's say, investments really to counterbalance the impact of the very high temperature. Unfortunately, the impact on energy and the impact on the environment is, of course, important, but is not the most important of the impacts of urban overheating. Actually, urban overheating affects very much low-income population. Low-income population is living in houses where really the environmental conditions or the thermal conditions are not really the most appropriate. No insulation, no double glazing, perhaps no shading. As a matter of fact, because of the low quality of the housing, indoor temperatures may be extremely high. And we have enough, let's say, proofs and enough evidence that people is living really under extreme indoor conditions because of the overheating. Do we have enough evidence about this? Yes. A very recent study performed, in Los Angeles, in the United States, has shown that there is almost a linear relation between the ground temperature and the income of people. People which really is of low income is living in areas with very high surface temperature, which means no vegetation. So people really of low income is living in areas which present a very high, let's say, ground temperature. But we have more evidence about this. And another study has shown really an important discrimination between, let's say, the area that we live and the income. For example, this study that was performed in the United States shows the relation between income of different, let's say, groups of people against, the temperature, against urban heat islands, urban overheating. And you may see, for example, that White people is living, the blue one, in areas of much lower temperature, while people, of lower income or ethnic groups, they are living in areas with much, much higher, let's say, temperature. Is it enough? No. We have performed a lot of measurements in low-income housing during the very last years, and I'd like to show you some of the measurements, for example. In Greece, during a heat wave, while at the beginning of the heat wave, study that was performed in about 400 let's say, low-income houses, showed that while the temperature at the beginning was close, let's say, to 25, 26 degrees, excellent, after 5 days of, let's say, heat wave, temperature, in average indoor temperature was close to 35 degrees, and we had, let's say, more than 50% of the buildings with indoor temperatures more than 40 degrees. The same in Sydney. Temperatures not during a heat wave, maybe during summer, more than 40 degrees. And at the same time, the concentration of CO2, because they close windows, they close the doors, they close everything, maybe, let's say, 3 to 4 times higher than the pressure. So because of the overheating, low-income people is living really under non-acceptable indoor conditions, and this is a problem. And this brings us to the serious problem of overheating, the problem of health. The problem of health is not a linear relation with temperature. It depends very much on several parameters, especially on demographic parameters, socioeconomic parameters, and the health infrastructure in the area. In average, we know that actually people is living in the more, let's say, warm areas of cities. They have 6% higher risk to, let's say, die because of compared to those that are living in the coolest part of the city. 6% higher risk really of heat-related mortality. Yeah, sorry. At the same time, there is a lot of work that has been done during the very last years trying to understand the impact of overheating on, let's say, heat-related mortality. Is it just the outdoor temperature that affects the, let's say, the magnitude of heat-related mortality? No. We know that while, let's say, the impact of the outdoor temperature on heat-related mortality is close to 6.1 deaths per million because of the high temperature, when this is combined with higher indoor temperatures, this is increased to 23.5, let's say, deaths per year. So this means that the combination of high outdoor temperatures together combined with, let's say, high indoor temperatures really is a very serious problem that may, let's say, kill a lot of people. You may expect that because of, let's say, the high temperatures, heat-related mortality has increased during the last years. No. Heat-related mortality has decreased during the last years. If you really check the statistics, I'm sorry. If you check the statistics, you will see that in most of the cities, during the last years, the relation between, let's say, mortality, heat-related mortality, and temperature is negative. Why? Because we are adapted. And this is not a physiological adaptation. This is an engineering adaptation. We have more air conditioning. We have better breathing. So this is what is happening. Unfortunately, this trend seems to reverse during the very last period because of the very high temperature. And the actual, let's say, predictions from Lancet and the group of experts shows that for most of the areas, and especially the Southeast Asia, the, let's say, expected increase of the heat-related mortality is really tremendous. And there's a decrease of, let's say, cool-related mortality or cold-related mortality. Are we sure about this result? No, we are not sure. Why? Because there is a lot of uncertainty about this issue. And this uncertainty is coming because of several parameters. Climatic model. We are predicting, the future using climatic models. In most, let's say, of the studies, we are using the more extreme scenario, but we're not sure about it. Second, the mortality model. We have established association between temperature and mortality rate. This association is based on past data. This past data will really be valid in the future? No, because we don't know how much really we will apply. And adaptation is very important. And adaptation is not only physiological, it's engineering. So we're not sure about the adaptation. And also we're not sure about the future population. So when really we try to be serious about the prediction of the future, let's say, mortality as a function of temperature, we may have a tremendous, let's say, uncertainty. And you see some results from a recent study. We may have a tremendous increase of mortality if we are not adapted, if climatic change is serious, if the population is increasing a lot, or we may have a small decrease of mortality if really we treat the whole thing in the proper way. So while the problem and the association between temperatures and, let's say, heat-related mortality is very serious, there is a very serious uncertainty about this issue. But it's not just mortality that is affected by temperature. It affects very much human health, and especially, the, let's say, problems, psychological problems, and mental health of human beings. We know, for example, very well that there's a tremendous increase of, let's say, assaults and murders as a function of temperature. The higher the temperature, the higher, let's say, the aggressivity. At the same time, there is a very interesting study that was published quite recently that counted and really evaluated the number of, let's say, aggressive tweets as a function of temperature. And you can see, for example, in this graph, that the higher the temperature, the higher, let's say, the aggressivity in Twitter. So this affects very much, let's say, the whole mental health of people. Is it just energy, environment, health, low-income people that is affected by, let's say, higher temperature? No. Human productivity is extremely affected by, let's say, higher temperature. Recent studies have really evaluated, using millions of people, that when temperature is increasing above 30 degrees, human, let's say, productivity may decrease by 60 or 70%. This is tremendous. Recent report published a month ago during the heat wave in India, in Delhi, where outdoor temperature was close to 50 degrees for about 4 or 5 days, shown that productivity in Delhi has decreased by 90%. You understand the economic impact, of this thing? This is what has happened actually. What do we expect for the future? Unfortunately, actually, there is a shortfall of about 330 million homes in the world. And we expect that during the next years that this, let's say, shortfall will increase by 440 million, let's say, homes. At the same time, the additional, let's say, housing needs will grow by more than 77 billion square meters of floor space, which is almost, the total floor area, the total area of China. You understand that we need tremendous, let's say, new areas for housing because of, let's say, the overpopulation and the needs, for proper housing. And most, of these new developments will happen in, let's say, in developing countries, India, Indonesia, Brazil, etc. In brief, this is very important. We build 1 parish per week. This is the rate of new construction. 1 parish per week. What does it mean, this tremendous increase of construction activity? It means that something will change in our cities, not because only of the overpopulation, of the regionally global climatic change, but also of the human activities. All models we have shows that by 2050, the temperature of the cities during the night period may increase up to 5 or 6 degrees. It's not the same everywhere in the world, but this is the average. In some places, the night temperature may increase up to 7 degrees. The daytime temperature may increase by 3 or 4 degrees. All models agree that in the future, our cities will be much more warm. Which is the energy impact of such a development? Cooling. We have a tremendous increase in penetration of the air conditioning in the world. using different models, different studies have shown that by 2050, the energy consumption of cooling in the world may increase between 1,620% up to 2,270%. Do you understand this? The energy impact, the economic impact, the environmental impact, the emissions impact, the, let's say, financial impact. Just one city of India, Mumbai, may present higher electricity consumption than the whole United States by 2050 because of the air conditioning. And the cost, of course, of this overheating is tremendous. It is actually 500 to 700 billion American dollars per year. This is the cost of the overheating. And it is expected that it will increase up to 1.3 trillion American dollars by 2050. So the cost of inactivity regarding urban overheating is tremendous, actually. But it's not just the energy problem. It is the social problem which is associated with the energy problem. If really we see and we examine the penetration of air conditioning in 4, let's say, developing countries, Brazil, Mexico, India, and Indonesia, as a function of the income of the population, you will see that there's a tremendous penetration in high-income population and a small, let's say, penetration in the low-income population. So by 2040, it is expected that about 1 million households just in these 4 countries will not have, let's say, proper air conditioning and will live at temperatures higher than 40 or 45 degrees the whole year. And of course, this has a tremendous impact, of course, on the energy consumption. So the social stratification, which is, let's say, generated because of the overheating and the consequences, the consequent financial, let's say, development will be, let's say, very important, especially, for the low-income population. So we have condemned a huge part of our population of the world because, of the overheating, because of the non-financial development, and because of the many other things. These are the bad news. Sorry about the bad news. Do we have really good news? Yes, we have good news. During the last, let's say, 15, 20 years, there is a very important research that has been carried out regarding, let's say, mitigation. We have developed techniques, we have developed technologies that can decrease the temperature of the cities. Of course, I don't have the time to go through all the technologies, but I'd like to show you some developments that, let's say, has happened in our lab, trying really to decrease the temperature of cities. One of the major developments that has been achieved during the, let's say, the last 5-6 years is the development of the so-called photonic materials for buildings. Materials that present a very high reflectance to solar radiation, more than 95, 96, 97%, but at the same time, a very high emissivity in the atmospheric window. So these materials may, let's say, reject the excess heat directly to the space through the atmospheric window. So these materials that has been developed, and I will show you some of this development, for example, the development of the first generation materials that we had in Sydney, which, let's say, were composed by, let's say, 2 layers, a reflector that really reflects the solar radiation, and at the same time, a material which is optimized in order to emit in the atmospheric window. These materials that have been developed and have been tested in the Australian desert present during the day under the sun, under the Australian, let's say, desert, subambient temperatures up to 9 degrees. It's a natural air conditioning. For example, why? The ambient temperature under 1000 watts was 35 degrees. The temperature of the materials was 26, 27, 28. So it's a natural air conditioning that when used, in cities may, let's say, decrease the temperature. Is it simple really to apply these materials? This was the first generation of materials. During the very last period, we have developed much simpler, let's say, materials. One material that was developed together with UCL in London, it is a new paint that we have developed which is composed by two materials, let's say PDMC, and at the same time, polyethylene. So we have created a new paint that really can be easily applied in any surface. And when really tested this material, it presented under the sun and, in the Australian desert, up to 3 degrees lower surface temperature than the ambient one. So we have really materials now that present very high efficiency and may decrease the temperature of our cities. However, there are important problems associated with this kind of materials. First, we have very high reflectance, 98%. You can use these materials on pavements, on facades, very reflective. Second, these materials are really white. We cannot have white surfaces everywhere. Third, there's an aesthetic problem. And third, if you like, the problem is that when these materials are used in temperate climates, increase, the heating energy demand. So we have seen that really we need to modulate the optical properties of the materials, because these materials may offer, a tremendous cooling potential, but may, let's say, present some problems during, let's say, the winter period. But once really we are able to modulate the reflectance, so the materials present high reflectance during the summer, a low reflectance during the winter, and at the same time modulate the emissivity, have a high emissivity during the summer, a low emissivity during the winter, or both of them, we may have win-win conditions. Decrease the temperature during the summer, increase the temperature during the winter. Smart materials. How this can be done? How really it is possible to decrease the reflectance and at the same time keep the same low temperature? What we have done is that we're using, together with photonic materials, fluorescent materials. These fluorescent materials absorb, in low wavelength up to 450, but emit immediately, almost 90% of the absorbed solar radiation in other wavelengths. So in this case, we may, let's say, have polar materials which present a low reflectance, but at the same time may have an additional cooling, let's say, mechanism. We have prepared these materials by using a combination of photonic and fluorescent, let's say, techniques. I don't really have the time to go to give you more, let's say, details. But I like to show you, let's say, these materials and also show you the results. This is the comparison under the Australian desert of the color, let's say, yellow photonic fluorescent materials against, the white materials, the white photonic materials. You can see that by adding color in these materials and also fluorescence, we have exactly the same temperature. So we can have color materials which present, very low temperature, similar temperature, like, let's say, the photonic materials. However, what is really amazing is that these materials, the color materials, present almost 4 degrees lower surface temperature than the white materials, the conventional white materials. So now, for cities, we may have color materials for facades, for pavements, for roofs, where really we may have, let's say, very low surface temperature, which really may contribute to, let's say, mitigate urbanism. And these materials may, let's say, present up to, let's say, 0.2 or 0.3 or 0.4 degrees higher temperature than the very advanced photonic materials. So these are very, let's say, materials of very high, let's say, potential. In conclusion, the recent developments we have on mitigation technologies has allowed us from a potential 10 years ago to decrease the temperature of cities close to 0.5 degrees, now to decrease the temperature of cities up to 2.53 degrees. We have more than 250 cities where temperature has been increased by 2.5 degrees. Actually, the development, of the photonic and the fluorescent materials has allowed us to decrease the temperature of cities up to 4.55 degrees. We have the chance to coordinate the biggest mitigation project in the world in Riyadh, in Saudi Arabia. By using these technologies, advanced technologies, we have calculated that we can decrease the peak temperature of the city up to 4.5 degrees. in collaboration with LBNL, that's in Hong Kong, we have calculated the energy impact of about 3,323 buildings downtown the city. And we found that it is possible to decrease the energy consumption of this building in Riyadh by 35% by using this mitigation technology. The study has been finished, and now we implement this project. In about 3 years, we will know the exact results. At the same time, similar studies in Sydney have shown that by using these techniques, it is possible to decrease the energy consumption in the city up to 29% when the materials, are considered at the, let's say, building scale. But when we consider at the same time a large implementation at the city scale and at the building scale, the energy consumption for cooling may decrease up to 49%. So there's really hope. What is also very important is that actually the use of these materials in low-income houses may decrease indoor temperature up to, let's say, 9 or 10 degrees. And this is not a computer simulation. These are real results that we have obtained through, let's say, monitoring. Also, calculations performed all around the world have shown that when really these mitigation technologies are used, we may decrease heat-related mortality up to 19.8% per, let's say, degree of temperature drop. So there is a win-win situation that really decreases temperature, decreases energy consumption, decreases really heat-related mortality. Similar results are obtained also for additional greening. Conclusion. We have the technology to decrease the temperature of cities. We know the question is why we don't really implement it. Because those that they govern, they really understand the whole issue by using financial, let's say, terms. So most, of our leaders, they like to monetize the cost really of overheating. And as I mentioned to you before, the cost of the overheating actually is, the cost of overheating actually is close to 500 billion per year and will increase up to, let's say, 1.3 trillion by 2050. So who is paying this cost? Taxpayers? Why this has to be distributed between all the taxpayers? Are we responsible for what is happening? No. In order to solve this problem, we need to develop financial mechanisms in order really to find the proper, let's say, resources to finance proper mitigation technologies. It is impossible really with the actual budget we have in cities and the budget which is spent by the states to, let's say, finance mitigation technologies. The actual cost of, let's say, decarbonization is close to 1.6 trillion per year from now to since 2050, and this money do not exist. So in order really to finance this specific, let's say, effort, we need really to push the financial sector to enter the game. This can be done. This can be done by creating a new market, a market that really will first take care about the quality of building spaces, etc., technological problems, but at the same time, will put a value on the urban mitigation adaptation capital. Those that they really increase the temperature in cities, they have to pay. Those that they increase really the temperature in our urban environment, they have to pay. And those that they decrease the temperature in our cities, they should really benefit from the credit. So we have to create a new market. So those that really, they don't care about what is happening in the environment, they don't care about the overheating of cities, that they build new buildings without really taking care of the overheating. Those that they use whatever materials, like asphalt everywhere, those that they don't really consider the anthropogenic heat, they have to pay the cost of the heat. And those that they take care and they build, low temperature, low energy, let's say new developments, they need really to have the credit. So by creating such, a market, we may, let's say, push the whole mitigation technologies in the world. How this can be done? Unfortunately, the building sector is very much fragmented. Technologists, energy experts, they do their research. Epidemiologists, they do their research. Energy people who's doing, let's say, it's research. Economists, they do the same. You know, so we're fragmented, and we don't have, let's say, good communication. So the whole, let's say, effort actually in our cities is not holistic, is not integrated. If really we wish to face the problem of global climatic change and local climatic change, we need really to integrate our effort to have, you know, an holistic approach. And this is my last slide. What really happens around the world? We know very well that we have a serious problem of overheating. This is extremely well documented. We know at the same time that there is a very important scientific knowledge about implication. We know that we can decrease the temperature of cities. We know that we have the technology. However, most of the implemented mitigation strategies are based on empirical knowledge. Let's plant a tree somewhere, let's change something somewhere, not scientific knowledge. Empirical knowledge that do not really contribute to decrease the temperature of the city. We know very well that politicians and, you know, those that they really take decision makers, they like very much simple solutions. For example, just planting trees. But this may have an impact that is not really a scientific approach that may decrease the temperature. So the lack of the proper policy in our, let's say, cities is increasing and aggravating the problem. Temperature in cities is increasing almost everywhere around the world. How to face the problem? First, we have to understand that this is a multidisciplinary problem. It's not just a technological problem. It's not just a medical problem. It's not just a financial problem. It's an holistic, integrated problem. And we need really to act in a combined way. And the last and the most important, if we don't really fix it, if we don't really proper measure, the impact on energy, on environmental quality, on low-income population, on mortality, on health, etc., will be really tremendous in the future. So what we need really to do is first to design, integrate, and holistic mitigation policies which are based on scientific knowledge, because there is scientific knowledge and not just on empirical approaches. Thank you so much.
Thank you so much, Professor Santamouris. So we have more than 5 minutes left. And Professor Santamouris explained how the overheating of urban heating impact our human beings, how it impact our economics, society, energy, and also our health, and also give us some solutions to mitigate the heat. And maybe we can also establish some overheating market to counterbalance the urban heat and other solutions. Maybe we also need to rethinking how we should do and how we can do in the future. Thank you very much for your impressive presentation. So maybe we can have several questions for the wonderful presentation. Yes.
Thank you, Professor. That was a really interesting and eye-opening presentation. I am just concerned about the materials that you were mentioning. They do serve their purposes, but I just want to know, how have you considered the environmental impact or the embodied energy of those materials?
The embodied energy of these materials is, let's say, maybe much lower than the embodied energy of conventional materials, you know. But materials will be used all the time, you know, in the built environment, you know. So embodied, the potential increase of the embodied energy of, let's say, alternative technologies is much, much lower than the decrease, of the energy that may, let's say, create. So embodied energy is very important, but it's not the major issue. It's not the major issue. The major issue is overheating and the increase of the temperature and the consequent, increase of the energy consumption.
Thank you.
Thank you very much, Professor Matt, for a great presentation. So I have two questions. So first is that you mentioned that in a poorly designed city, the overheating can goes up more than 300%, and this is very eye-opening. Could you please elaborate a little bit more about this? So what mechanism of this? Is that the concentration of the heat was because of the poor urban ventilation or something? And also, could you please elaborate a little bit more about the features of the poor designed cities? Because that's something we are really curious, because in a city, sometimes people will think that they all look very, very similar, but in your presentation, you showed that in a poorly designed city and a well-designed city, the overheating can be really, really diverse. What do you think is the key features of the poor designed city that cause such devastating overheating? Thank you.
I'm not sure if I have understood completely, your question. Actually, in the reasons of overheating, let's say in cities, first of all, the very high absorption of solar radiation by the structures, and building pavements, whatever it is there, because we are not using the proper materials. Second, anthropogenic heat, which is, let's say, very important. At the same time, phenomena which has to do with, let's say, the lack of ventilation in the city, and also, let's say, greenhouse effect that does not allow the, let's say, infrared radiation to escape. So these are the reasons, as I mentioned at the very beginning, the overheating, let's say, period in most of the cities, almost all cities, has increased by a factor of 3 during this period. So the problem of overheating of our cities is a real problem, really problem. And it's extremely well documented at the same time and is increasing continuously. On the other hand, all, let's say, simulations we have for 2040, 2050 shows that, in the future, let's say in cities, the temperature increase, during the nighttime will be very important. Not so much, let's say, the maximum temperature, but the minimum temperature, the nighttime temperature, 6-7 degrees, this may have a tremendous impact on the energy balance of cities. Why? Because buildings will not, and the structure will not be, let's say, cooled during the night period. So the temperature will be accumulated. At the same time, most, of the passive cooling techniques we're using, night ventilation, etc., will be very much affected. Third, and this is very serious, because of the very high, let's say, temperature during the night, the peak electricity demand is transferred during the night. And this happens now in Europe. What does it mean that? It means that during the night, we don't have photovoltaics. So in this case, and especially during heat waves, we don't have also wind speed. We don't have wind energy because during, let's say, heat waves, the wind speed is very low. So during, the extreme phenomena, you don't have renewables, or you have very low renewables. In this case, either you need to have a very high, let's say, storage capacity, which means money, huge infrastructure, and huge cost, or you need to operate, conventional energy sources. So this is a serious problem that increased tremendously the cost of energy provision, in cities. This is the main problem that we are facing.
Thank you so much.
Okay, maybe one more question.
Thank you very much. Hey, Matt, very impressive presentation. You have one interesting slide, talk about charge tax for heat emission from the building. So what about those heat emitted from the AC, air conditioning systems? how do you charge tax for those heat?
Can you repeat the question? I'm sorry.
Okay, you have a slide. You have a slide showing like building emitting a lot of heat. You talk about probably taking penalties for those heats, right? So we have a lot like Shanghai, for example. We have a building using a lot of AC, and then the AC also dumping a lot of heat to the urban area. How do we charge tax for those heats?
I'm not saying tax. I have not proposed taxes. I have proposed
You have one slide showing like we should like
credits. Yeah. I will explain you.
okay.
This system, applies already for the decarbonization all around the world. You have the carbon taxes and you have the carbon credits. You have ESG. For example, all companies that really they produce, let's say, a lot of CO2, they have to buy, let's say, carbon credits. And what they are doing is that they are going to Indonesia or to India, I don't know where, in Amazon, and they plant trees. And I'm not sure if such, the carbon credit has any impact on the environment. Because first, you will get, the result in 20 years. You're not sure if really, after 20 years, the forest will be there. So there is a serious problem, actually. So what I'm proposing is to transfer this mechanism, financial mechanism of, let's say, that applies on the decarbonization on urban overheating. For example, in new cities around the world, you have new developments, new settlements. They don't care at all about overheating. They just build the very conventional way. They increase the temperature in the area, and this impact, financial impact, is paid by the taxpayer. On the other hand, you have the possibility, because the technology is available, to build and decrease the energy consumption, the carbon emissions, and at the same time, decrease, the potential overheating, mitigate. So shall we really treat the same way both developers? No. Those they don't care, they need to pay the cost. And those they care, they need to have benefits. How this can be done? This is another discussion. I can explain you. We can easily, let's say, count the sensible heat, which is emitted by, let's say, a structure. So by counting the sensible heat, we can have fines and carbon credits or overheating credits. This is a system that is going to be applied, since next year in Europe, in the 100 zero carbon cities. So I think that if we don't really impose or specific measures to those that they don't care in the built environment, we will not succeed really to improve the quality of our cities. If we allow those and we permit to those that they don't care about the quality of the urban environment to continue building this way, we will have, let's say, cities by 2050, which will present, temperatures up to 5-6 degrees. And in this case, the reactive measures will cost 10 times higher than the proactive measures that are really proposed now.
Thank you. We can talk more afterwards. Thank you.
And thanks all your participating, and we have a gift for your great contribution. Oh, it's coffee break. Thank you. Thank you for participating.
是下一页是哪里？下一页是这个短的，是上一页这个都可以，都可以用，就在这里。
Hello. Okay, good morning, everyone. Sorry for late, because I was assigned to a chair in another section, so I went there, and I used the old version. So I was told that I was the chair of this section. So I'm sorry for the late. And we have, in this section, we have 4 invited speakers. And we will start from the first speaker, Professor Zhu Yinxin. I don't think I need to introduce you because everyone knows you. So Professor Zhu's topic is rethinking the method of building indoor environment for carbon neutralization. So let's invite Professor Zhu to give us a talk.
Thank you, Chair. You can see the topic of my presentation. In fact, I'm going to share some of my ideas with you. Maybe this idea is related in future building simulation. Now I show a picture of the world building energy consumption. You can see, in this picture, you can see energy use intensity per capita and energy use intensity per floor area. Both of the indexes of China are much lower than Western countries. And now China also set a target to be a carbon neutral by 2060. Here is figures of the global share of building energy consumption and the global share of CO2 emission from buildings. You can see in both indexes, the building sector all share more than 1/3 in the global energy consumption and global CO2 emission. So in this case, we all know that building share the largest, building sectors share the largest part of the building emission, CO2 emission. So how building sector meet the new challenges, especially in China, I think also the problem in the world. So in this case, we should keep the tenet is indoor environmental quality should not be reduced by carbon neutrality, but should be further improved, or the people occupants will against this target. So there is 2 main strategies we should adopt. The first strategy is building energy supply side reform. It includes 2 parts. The first part is with the decarbonization of power grid. The building will be electrified. And the second part is make full use of renewable energy, zero carbon energy, and waste energy. I think everyone knows that. And also Chinese strategy in next step. And the strategy 2 is reduce building energy demand. The first one there is everyone knows that the passive low energy design is need collaboration between architect and engineers. And also another one is very important. Today I will focus provide precise thermal surveys for indoor objects. Okay, from this view, we have, I will introduce three rethinkings. The first one is, what is comfortable environment? Is thermal neutral equal to thermal comfort? Now, until today, the indoor environment standard is still PMV in all of the country, all over the world. And this PMV is invented from steady state uniform thermal environment rather than the real environment, in fact, because it is obtained from the climate chamber experiment. So based on the standard, for example, this one, the ISO 7730, it means the better, the narrow range, thermal environmental range, the better. The standard shows that. Is this good? So I will show you some pictures. These pictures is very common in Southeast Asia and also very common in south end of China. For example, in Hainan province, there's a very high class of hotel. It's a common zones. There are no wall, of course, no air conditioning, but they are in the tropic area and they are very high temperature, about 30 degrees all year round. They no air conditioning, no wall, but people think it's comfortable. Why? Just now is a relaxed environment, but I show you this working environment. This is an example of an office building in Shenzhen. And this office building has, there is a conference room. The conference room, they have a whole external wall can be entirely opened. This figure shows in November in a year. In November, in the morning, there are 4 seats, only natural ventilation, no any cooling, no air conditioning, no cooling. Outdoor temperature is 24.6. In fact, only if you supply fresh air, outside air, this temperature is still too high. But by natural ventilation, people feel very comfortable. In fact, in this area, Shenzhen is close to Hong Kong. Even in November, you know, this kind of a conference hall always fully air conditioned in this area. But this building can fully use fully natural ventilation. People will feel very comfortable. This building also has a platform between every floor, and you can find the people there as make this cooling water, the meeting, group meeting. They're not drink coffee here. It's working. Discussion is working here. There is 2 groups there during this daytime. They discuss there. We do the measurement. You can find the temperature outside is around 30 degrees, and the humidity also quite high. Of course, this warm environment. We do the questionnaire. The people vote. We ask them to compare the air conditioned indoor the office and outside platform. They always vote the open terrace is warmer. Then office, air conditioned office, but the open terrace is more comfortable. Now, another side, more comfortable than the air conditioned office. Although the office is neutral, it's more neutral, but not as comfortable as the outside. Why? This is very interesting. Oh, why outside? To confirm this finding, my student also studied the outdoor, do the outdoor thermal comfort survey, and you can find that the people vote neutral, comfortable, and very comfortable more than uncomfortable and very uncomfortable. Of course, the people who work outside or stay outside, they prefer the outside environment. But anyway, my student get this thermal comfort zone for outside, outdoor. You can find that the outdoor comfort zone is much larger than the thermal comfort zone in the nature ventilated room. This is actually thermal comfort zone for the nature ventilated room. But this one is outdoor comfort zone. The green mark is shading environment. The red mark is under the direct solar radiation. So this situation is very interesting. So we believe there is the effect of the nature ventilation, nature wind. So in fact, our team, Tsinghua's team, spent more than 20 years studying the role of nature wind. To compare the natural wind and mechanical wind, you can find that we use turbulence statistic and chaos analysis, and use the continual wavelet analysis. You can find the mechanical wind and the natural wind has obviously significant difference. And according to this finding, we developed some terminals, different, at least there's two kinds of terminals to generate different kind of airflow, include the simulated natural airflow, natural wind. This one is a constant airflow. This simulated natural airflow. Another one is a sinusoidal variation airflow. I mean the air velocity. Of course, in the neutral environment, 26-degree environment, the people prefer the constant airflow. And about the draft, they feel not so different. But during the environment of 30-degree, the warm environment, the people prefer more the simulated natural airflow, the red one, and they feel under the simulated natural wind, they feel neutral, thermal neutral, and they have the least draft. So it's a very interesting. So I have to think. Think about what is comfort. Comfort comes with the elimination of discomfort stimulation. Once the uncomfortable stimulus is gone, comfort is gone. And the comfort can be maintained only when moderate stimulation is keeping present. And this a kind of a dynamic thermal environment, just like outside in the spring, a comfortable outside environment, like this. And the outdoor environment parameters are changing continuously. Wind speed, solar radiation, temperature, humidity, they always keeping changing. How to say that? Gently changing. So this field, this variation, we call it alisthesia. So it's a comfortable environment. And the rethinking too is what is a healthy environment? Is constant thermal environment equal to a healthy environment? In fact, the human body has the ability to adapt to the thermal environment. Long time staying in the stable thermal environment may weaken this ability with negative health effect. To confirm this hypothesis, we do the experiment like this. Use a climate chamber, and to study the impact of long time staying in stable neutral environment on thermal regulation. We recruit two groups of a young person, all males, ages 20 to 30, and they all well educated, but have the college educated, and so their work is a white collar work. The first group we call the AC group. They both were working place and residence with air conditioning. In the last summer, they spend almost 24 hours a day in the air conditioned environment. And then another group that we call natural ventilation, NV group, they spent less than, in the averagely, they spend less 2 hours per day in air conditioning environment. And they was put into the climate chamber, stay in 26 degrees for 1 hour, and shift to 36 degrees for another hour. Then they do the psychologic test and subject voting, and do the physiological test different parameter. And I show the result here. When the AC group entered the high temperature 36 degree room, they shows the vote warmer and more uncomfortable. There's a thermal sensation and thermal comfort vote, and their skin temperature responds slowly, slower than MV group. And the temperature difference between chest and feet is higher than MV group. And their sweating volume over the whole range of BMI are lower than the MV group. And also they has a higher HRV representative excited sympathetic activity. And this index is more important, is heat stress protein 70 in the blood. Between the before the experiment, after experiment, they have been blood sampled. Because the higher HSP 70 in blood shows a stronger thermal adaptability. You can see MV group, the difference between MV group and AC group. AC group's HSP 70 is just 2/3 of MV group. That means long time staying in a stable neutral environment results in degradation of thermal regulation. And there is another experiment doing by the Netherlands researcher, Professor Wang Macken-Lichtenbell. They do the mild cold exposure experiment to see the relationship of cold exposure and the diabetes. The cold exposure is environment temperature is 14 to 15 degree, 10 days cold exposure each day for 6 hour exposure. You can find that they have two group subject, and the one is a lean young adults. They are brown fat tissues increased. You can see from that figure. And also their energy metabolic rate increased to higher expenditure. Then after the 10 days experiment, they feel the cold environment is comfortable, acceptable. And another subject is male patient of type 2 diabetes. And they after the experiment, they found that the insulin sensitivity increased by 43%. So Professor Lichtenbell concluded that need to exercise our thermoregulatory system as a part of a healthy lifestyle, increase resilience to more extreme weather conditions. And anyway, their experiment is a climate chamber. So I would like to find a real example in the real life. It's very interesting that in China, we have in North part, we have the central heating system, and now South China, there are no central heating system. My student do the on-site experiment and also collect all the other Chinese researchers survey the data. We found that in the indoor temperature of a central heating house and in south part of China, the non-central heating house indoor temperature is very different, at least 5 degrees difference. So we think maybe this one can find some something can support Professor Wang Lichtenbell's chamber experiment. And because in the south of China, in winter, the indoor temperature range is just Professor Wang Lichtenbell's experiment temperature. Okay. So the first step to the provincial scale experiment, collect the data from Chinese data we call the tide data. We found that the temperature province standardized prevalence rate of diabetes. Maybe you cannot see something because this province name in Chinese, but you can find that the central heating exposure level is a standardized per capita central heating floor area. It has the relationship, positive linear relation with the standardized prevalence rate of diabetes. But anyway, the diabetes factor is so large, so we have to do individual scale analysis. This data is from not the Chinese diabetes data source is called CHARS database. After doing if you are interested, you can find this our publication. After controlling of gender, age, BMI, smoking, alcohol, and socioeconomic status, the indoor thermal environment in winter still remained significantly associated with diabetes. Of course, there's the data is from different cities. My student also, in the past 3 years, she do the on-site investigate to the house and the individual in the same city in China. And in the same city, they also has a central heating area and non-central heating area. They are mixed together, so she do the comparison, also find the difference, the exposure, mild cold exposure, and the diabetes. So we will publish this result in near future. The rethinking third is how to build indoor environment, uniform and food space, and the PCS. We do the on-site investigation on the central heating and decentral heating using Beijing. because in Beijing, the decentral heating is your household boiler. In the central space heating, the users cannot control our room temperature because we can open the window, it's too warm. But the decentral space heating user can control their room temperature. It's very interesting that we found that in the decentralized heating, the two on-site investigation, both the result shows that the decentralized users, they have a lower neutral temperature and a wider comfortable range and less energy consumption for space heating. So this, I think this occupants perceive controls effect, because once occupant have the perceived control ability over the environment, whether they use it or not use it, they will their satisfaction and the tolerance to the environment will be greatly improved. Because the anxiety of unknown changes will be eliminated psychologically. And humans' physiology has the thermal regulation ability to the thermal stress, and the environmental tolerance is very large. But if the environment controlled by outside force, this kind of this kind of ability will be decreased. The tolerance is weaker. So we also always see this case that in the same environment, someone feels too warm, someone said it's too cold. This due to the diversity of the thermal, the human's thermal demand. So what is the best indoor thermal environment quality? Is PME equal to 0? Not, because the PME is a statistic of many people, many subjects, not personally. And we all know the first air conditioning system invented by Willis Carey in 120 years, 20 years ago. But you should remember that he developed this not for our thermal comfort, it's for industrial process. So he had to keep the environment uniform and full space, the uniform parameters. But when we use this theory to the thermal comfort environment, we should remember the diversity of the individual. So I believe that future development trend of air conditioning or HVAC, indoor environment control, as a personal comfort system, we call it briefly PCS. The air conditioning system just keep a surrounding ambient quite loose, and everyone. This one like a cooler environment, that one like a warmer environment. They can use PCS to keep their personal system. And there are different kind of PCS. This one is chair. Cooling or heating chair. That one's Tsinghua's contact cooling chair. There's UC Berkeley's ventilation chair, and Professor Funger's personal ventilation system, and our body cooling garment, and foot heater, and the leg heater, and there's a hand warmer, neck cooler, and the Japanese kotatsu. The Japanese kotatsu is a very traditional personal comfort system. Because and we, according to our experiment, we found that when the ambient environment, 30 degree is quite high, 30 degree, the neutral surface temperature of the chair is 26 degree. The people will feel generally 26 degree. Sit there, you feel neutral. And another experiment about the garment. Use a PCM, a phase change material. Phase change material temperature 26 degree, and the ambient temperature is 30 degree. The subject wear this garment, it feel he or she will feel the neutral. The subject is me. So in this case, we can expect high temperature cooling as a cooling source. When we use a high temperature cooling source, we can get the advanced as a high COP. The traditional air conditioning system, the COP, the temperature range is from 5-degree evaporation and to the 45-degree condenser. So the whole system COP is always lower than 5. Not mean the chiller as a system, HVAC system COP is less than 5. But if you use a contact body cooling chair, we just need the temperature is 24 to 28 degrees. So in this the much lower heat flux and the total cooling capacity is one chair is 15 watt is okay. So in this case, the theoretically invert Carnot cycle COP can be very high, much higher than the past. So through the building simulation, we can get the cooling, heating, energy consumption with the set point. We found that if for the public or commercial building in Beijing, if the indoor set temperature increase from 26 to 30 degrees, the cooling demand will decrease by 77%. If the heating set point from 22 degree decrease to 16 degree, the demand, the heating demand decrease by 68%. Is huge, I think. In Beijing, we do the on-site investigation studies. The data shows that in the summer, the Beijing office building, the electric consumption in summer is about 40 kilowatt-hour per square meter. If we use this kind of chair, even the COP of the chair is just 5, and the power consumption is per chair 3 watt. The cooling demand decreased by 77% because of the ambient temperature increased to 30 degrees. So the total energy consumption for the office will reduce to less than 10 kilowatt-hour per square meter, just a quarter of the original energy consumption. So why not promote PCS as much as possible? Because it's too difficult. Even for heating is easier, but there are still many problems to be solved. That's this government we developed in my group, leading by Professor Cao. And the problem is how and where to heat, and how to make the power bank last as long as possible, because this warm government need the power bank. And for cooling is most difficult. This one is we need the high temperature refrigeration, but the micro refrigeration or heat pump technology is not mutual. It's a lack of applicable technology, or expensive, or low COP, or temperature is too low. And also another problem that how and where to cool. This is a healthy problem. But there are some new progress may make this possible. This data is from the Professor Li from Department of Material Science of Tsinghua University. He shows his new experiment. It shows the COP of the semiconductor refrigeration technology can be close to a COP close to. And in this case, is competitive for PCS application because the current is related to the heat flux. If we use the cooling chair, the heat flux is very low, not so high. So the COP can be high. So this is a material science. So collaboration cross discipline is necessary for the micro refrigeration technology. Okay, finally, I will give the final conclusion. I mean the trend of a new future development is PCS, but we can meet the problem, new challenges in building simulation as how to predict the total energy consumption of PCSs. And if they use multiple type of PCSs, it will be even more complicated, more difficult. And how to describe the personal demand with more diversity. This is a problem as indoor parameter. How to describe the indoor parameter? What are the representative value of the indoor parameters for the indoor space? Can lumped parameters model be used for all occupants' individual environment? In this case, is a zonal model necessary? This is our problem in the future, more complicated. Okay, thank you for your attention.
Okay, thank you, Professor Zhu, for your wonderful presentation. So consider the time limitation. Shall we take one question from audience? Any question? One question, please. No? No question? Oh, I think it's fine. Wait a moment. Rush. Okay, thank you, Professor Zhu. And now we invite our second presenter from Cyclos University, Professor Bin Dong. And his topic is from machine learning to quantum computing, future smart building control and optimization. So let's give the time to Professor Dong.
Yeah, thank you. Good morning, everyone. My name is Bin Dong. I'm a professor from Syracuse University, Mechanical Aerospace Engineering. I'm also associate director for Syracuse Center of Excellence in Energy Environmental System. Today, I'm giving a topic on the machine learning and quantum computing. I'm not going to give the talk on occupant behavior, which is I've been doing this work for the last 10 years. So why building control is very important. If we look at all the energy systems in the commercial buildings, whether it's HVAC, lighting, product loads, everything, it needs control. And also the previous study is showing that 15% of energy actually is wasted if you don't have a good building control. So that's why we have to treat building control very carefully. And if we think about a bigger level, like urban scale, smart homes, smart buildings, they all connect with power grid, including the power transmission distribution grid, and also power generation. Especially if you imagine in the future, if every building active as a very intelligent building, which have different controls, it will have a large impact on grid. So if we think about at urban scale, the building control has to be integrated with the smart grid controls to make sure the smart grid has stable voltage and frequency. And the other reason is if you look at the broader area of the building controls, there's communication, energy systems, there's the manufacturers, they all have control problems. And all of them are in the buildings. So building control is very important to maintain not only building science, but also other set of the energy asset or any asset in the whole city. So how we do building controls traditionally? I think everybody doing building control know this diagram. We started with heat transfer sound dynamics of the building, which you call the detailed modeling. And you can use enterprise model or Modelica models. But we have to convert that into the so-called control-oriented model. So from this theory, we developed so-called lumped RC representations. And this lumped RC representation will help us to derive the so-called state space model to design control. That's how we do. That's how all the control people will do, the state space model. And we know using this RC lump model for last 30 years, since 1990s probably. Everybody uses that until now. So what is the problem with this? Because in reality, how many buildings are controlled using this approach? I know one building in Berkeley is using MPC for 1 year. And we are running the lab using MPC for some time. And I'm not sure if any other building is running this model at all. In the reality, people have so-called rule-based controls, right? Looking at the weather forecast today, the facility manager will decide when to turn on the HVAC, when to turn off the HVAC. That's how it goes in reality. So what's the problem? The research has been done for the last 30 years. Why don't people use it? So if we look at the actual control problem, we are relying on a so-called linear time invariant system, LTI system, x naught equal to x plus bu, and y equal to x plus du. It's a typical LTI system in the control overview. So what is LTI system? Means it's linear, it's a time invariant. But in the actual build, it's very hard to capture nonlinear indoor environmental dynamics, like the change of temperatures, change of CO2. It's not linear. It's all nonlinear. And then there's a lot of mixed of continuous and discontinuous controls or control HVAC operations. Like say, I can turn off the fan. There's only 1 or 2 stages of the fan, right? It's not controlled continuously. Or sometimes I can continue control the point temperature. So the mix of a lot of different control variables, and it's not always a continuous system. It's not always a discontinuous system. So that's bring a very good challenge for the building controls. And also when the model become large, right? So this is a simple like 3-bedroom house. It's already very large. It involve too many control variables and the state variables. And the model calibration and control are both difficult. So when I say model calibration, when you have 10 unknown RNC values, you try to use a MATLAB. They have a calibration called Lincoln, and then you run the models. You input the measured variable. You calibrate 10 unknown variables. It could be any combination, give you correct results. You never know if calibration is correct or not, right? So that is a challenge when model become large. And also thinking about, this is just one building. If we have 10,000 millions buildings, you're not going to develop the RC model for millions buildings. When you talk about urban scale, buildings to grid integration, right? So that's a big challenge. You cannot even do matrix inversion in MATLAB when you have millions state variables. Even you do a matrix inverse, you cannot do it, unfortunately. So you cannot solve the control problem. So then people are starting to think about, okay, what about machine learning? Data mining, right? So use a so-called black box model, whatever is a neural network, support vector machines, or other latest machine learning algorithms, put into the model and then later run it. So, but there's a problem of those models are not control-oriented model. So those models, there's no physics information inside. It learns from the data. The data could be anything, garbage in, garbage out, basically. It's like simulation tools. And also, there's no global optimum guaranteed. You have to understand those models are like this. Those are the ones of those models. It could be stuck in the local optimum. We call the plateau. When your gradient cannot close to 0, cannot move anymore, it's stuck into the local. Okay. So what is a good model? So good model combined with machine learning is so-called physics informed. machine learning or neural network model. So with a fixed informed model, you basically put a physics laws into a training process. You add the physics constraints into a neural network. You ask your practice model understand that there's a physics behind it instead of just a purely data-driven model. So we developed two things. We developed physics-informed network model, which is combined advantage of physical model, which is RC model. It had the present physics of the building, and also the neural network model. The other thing is we also make it as input convex network, which is guarantee the global optimum for the optimum controls. So this is how we did. We look at still RC model, and we look at different metrics of the RC models, RC variables, and we call this a system metrics A, B, and E, input and disturbance metrics. And we start to look at MPC. So when we do the model pre-control, we do multi-step ahead predictions, right? So we start to construct this using the MPC way that we put different metrics into different steps. So, and luckily we found out that this structure actually can represent in the neural network structure. If you look at typical neural network structure, so it can represent like this. So basically, if you look at neural network structure, you can actually do not rely on the fully connected network. You can do partially connected network. Make sure it is partially connected and it can represent the prediction. And also, you can put the ABC matrix on the diagonal or the lower triangle matrix to make sure it represents the physics. And we also do three things. One is the correct input-out time correlation. So in the fully connected network, it says that when you do prediction, 24 hours ahead, the temperature will have impact on the temperature right now, which is not true. The temperature right now will impact temperature 24 hours ahead. And also we do shared weight, which is shared weight refers to the resistance patterns. And we do the descending norm. Descending norm is a typical strategy in the machine learning called attention. So we use the attention model to make sure the physics consistency and the input-out correlation. So after we do this, we basically this is the original model, and we use a neural structure to represent multi-step space model. So instead of using the physics RC model, we're using neural network to represent it. So why we use neural network? Because it will avoid the LTI system. Okay, so with that, we did a very interesting study showing using the three latest control algorithms. So we have a model, so-called PINN model, physics informed network. And then we use, the first one is called data-driven predictive control. The second one is a differentiable predictive control, DPC, and last one is reinforced learning. I think probably everyone doing controls knows these three methods. It's very popular right now. So first of all, look at the data-driven controls. So in data-driven control, as usual, we do occupancy prediction, we do weather forecasting, and then we construct this, we predict the indoor dynamics based on this PINN model, and then we do the controls. But there's pros and cons for the DDPC. The pros is there's no offline training. You have to do everything online. So you have to do weather forecasting, occupancy prediction, and do the controls, everything online. Okay? And then it's very accurate decision because it's based on the predictive controls, the PINN model and our plus predictive controls. And then you can also include user feedback in the loop. And the cons is feasibility issues. Because it's solved optimization problem, it's always has a feasibility issues, always. If you use optimization algorithm in the MATLAB or Python, when it's interior point method or other methods, you always have this feasibility issue. And then it's a high design effort because I need to design this based on my PINN model. And also online computational expensive. I cannot do offline training, I have to do online. So every time step takes 10 seconds. but we still do it because we want to compare the performance. So we design DDPC for hierarchical control. At room level, we reduce the space load. At the system level, we reduce the system load with indoor air quality as a constraints because we want to maintain thermal comfort and also indoor quality at a certain level in the space. So the second one is called differentiable predictive control. So differentiable predictive control, from the naming, you can know it's differentiable, means it has to be convex, right? It's differentiable. And this control is when you're making a decision, is model free. It has offline controlling, and then it makes the decision online. It's on computational very cheap. It's very fast from the control decision. It's more like agent-based modeling. So you have PRNN here, which is provides the indoor dynamics, and you have control law-based neural network here, okay, to make the decisions. And the whole process is trained as a large-scale neural network. You're using the image data to train this model and to make it learn. Okay, and next time, how you make the decisions, as long as you input the current or future weather forecast, indoor temperature, it can make the decision right away. And again, so this is on the upper level, it's a model-free control policy network. And then we minimize energy loss, minimize the poor operation loss as a training objective, okay, to train this model. This is a DPC. The last one is called reinforced learning. So reinforced learning is nothing but just a Markov decision process. It's been there for many years as well, applied into robotics, and then come to the buildings. And nobody changes the algorithm of reinforced learning. Everybody using the framework of reinforced learning, actually. So the problem is that it's an agent, the same as a differentiable predictive control, makes control decision leading to scalable solution. And it's a model free if you're training by the interaction with real environment. Okay? So you don't need to build you don't need to define the parameters. You learn from the environment and you keep training the model. And the cons is the reward design is very tricky, and it's difficult to train. And training convention is not always well guaranteed. Yeah. So in our case, we're using so-called soft actor critic as our algorithm for this agent development. I will not read this, but it has 3 networks: policy network, action value network, and state value network. We just make it work. But as you know, IL is a very difficult train, right? So every time my student train reinforced learning, he's like tuning the parameters, and he has a fire in heart because it's so difficult train, cannot find answers, right? So all his job is tuning parameters, which is very boring. So IL is very famous to difficult train, like the GAN model. GAN model also the same, very difficult train. You are literally hope and pray that you have found the best parameter and give best results. And next time you run it again, it give you different results because it's probably the best. Okay, unfortunately. Okay, so we use 1 month cooling season as kind of simulation study. Optimize any usage, maintain indoor environmental quality, which is CO2 level in the space under 620 ppm. So compare with 3 different control algorithms. And of course, all 3 algorithms can make all the indoor temperature and the indoor environment quality very well maintained, no doubt, right? They all works, right? But in terms of energy consumption, we found that there's a very little difference between DPC and DPC, but there's a large difference between the reinforced learning and other algorithm at system level. So that is because maybe my IL is not well trained. We spend many days to train this IL, but that's the results we get. Maybe someone else train it will have better luck. That's the uncertainty on IL. Yeah. So with that, I want to conclude on the latest machine learning based controls to solve building control problem. Those are the 3 latest algorithms people use, and all 3 of them works pretty well, and it can solve the scalability issues of typical RC models, right? So, but we also notice that they're all focusing on either a continuous problem or a discretized problem. And on a small scale, you never see a like test study showing that, okay, I have 100 VAB boxes. I'm using machine learning to do it. It's very, very rare. Okay. So back to this question. Yes, we use the PRNN to capture the nonlinear environment dynamics, which is very good. How about the mixed continuous discontinuous HVAC operations? We just still didn't solve it. That's the hardest problem ever. It's called a mixed integer program. And this is true in reality, right? So then we are looking at different algorithms. So for example, if even in the real world, it's more larger scale. So this is diagram from CTBS, and we developed this model for San Antonio, Texas, and we try to control 900 buildings and integrate with a smart grid. And we found out it's too large scale. You build even you use a 3R2C model to represent one building, you will have 2,000 control variables, and even 2,000 states or 4,000 states, depends. How you do that? Right? You cannot. And also, it makes a continuous discontinuous building applies the HVAC operations, because not all buildings has a centralized HVAC system. Some buildings have heat pump, some buildings has a rooftop units, right? It's not all off control. And most people use genetic algorithm, GA, to solve this problem, or based on optimization, or Groovy, right? So to solve it, Groovy is a very good tool to solve MIP problem. But again, because the larger scale, my student run GA for like a week to get the results, and he does not know if it is correct. It's very difficult. So what we can do? So there's one day I was reading one paper about quantum computing on the Nature, and then I think about, okay, what about we use quantum computing applied in the buildings, right? So this is a quantum machine by the Google. It says Google, just this drive. Google's quantum computing is 47 years faster than #1 supercomputer. 47 years faster. That's cannot imagine, right? Okay, so then I look at ask my students and postdocs look at how actually quantum computing works. So quantum computing has three very interesting thing and concept. First one is called a superposition. The other one is called quantum annealing and quantum tunneling. Three things. And in the quantum computing, what is superposition? So in the traditional CPU, we only have two states, 1, 0, 1, 0. Everything is based on 1, 0. Okay. But in the quantum world, it's called qubits. It's different. So what is quantum world means? So superposition means I have more than two states, 0, 1. It calculates in the multi-dimension space by quantum computing. So why this will happen? This is all based on this Schrödinger equation, which defines the quantum computing. Because imagine if you flip a coin, before the coin falls on the ground, it has many possibilities. Okay, but this one saying that my coin only have 0, 1. So it actually searches the whole space. And that's how quantum computing works. That's called a superposition. So next one is called a quantum annealing, which is very simple. The physics system evolved towards low NH to state, high temperature to low temperature, high potential energy to low energy. That's like the classical mechanics, right? So, but the other one is called quantum tunneling. So quantum tunneling is different from classical mechanics. In the quantum mechanics, quantum tunneling is based on the Schrödinger's equation that it can go through the energy barrier, and this how it can go through the energy barrier is because it's special character of the quantum electrons. So what's the special character? So in the classical mechanics, we all know the particles need to climb the barrier. This is how the gradient descent works. So when you do optimization, you're using gradient descent, and gradient descent can only do that. Okay, you found the lowest gradient and go next step. But in the quantum mechanics, quantum entities have both particle and wave properties. It's called wave-particle duality. In Chinese, it's called 波粒二象性. Yeah. So because of that, so you don't need to climb the energy barrier. You actually can tunnel the energy barrier. Okay. So that's a very special character of quantum mechanics. So because of that, so when you solve the optimization problem, you're not going to do the gradient descent, the classical way, but you are doing the quantum tunneling. And plus the quantum annealing, which is from energy flow, right? So you always found the global optimum solution instead of stuck in the local optimum. Okay, so that's a very special character of quantum computing. So we found this and we tried. So then how this can apply to the building problem. So it's different from you can call a Python package of neural network and then you just input data and run it. You have to reconstruct your problem mathematically. So I use so basically we use a D-Wave quantum computer, and this D-Wave is a Canadian company. And the D-Wave quantum computer can solve project unconstrained binary optimization problem. So basically all the problems you have to reconstruct into the binary or projective unconstrained binary optimization problem. So that's the D-Wave quantum computer can solve it. Okay. So if we look at one example of a packaged rooftop units control problem, it's a typical hard problem, mixed integer programming problem, because it has staged fan, it has staged cooling and heating, can be off during unoccupied period. So you now control, in a continuous way, right? So this is a typical MIP problem. What people normally do is it assuming continuous at a certain operation range, but didn't consider the big picture of like say, I can on off or turn off certain period for next 24 hours. Okay. So this is how we do. We reformulate the objective again is a minimize energy consumption. So we reformulate this objective function into a binary variables, and then reformulate this into the projective unconstrained binary optimization problem. You have to do some little math into it. So instead of core package, you have to reformulate this problem into that. So the D-Wave can solve it. So this is one application. And the results is pretty good. So this is a 6 hour, 12 hour, 24 hour precision height. The precision horizon is 6 hour, 12 hour, 24 hour. And look at the results, right? It's not continuous, discontinuous. Sometimes it's off, sometimes it's on. And if you compare with computational time with two very popular algorithms, genetic algorithm and Groovy. So the quantum computing, if we look at the 12-hour ahead prediction, like say, we do 12 hours of prediction per horizon and every 15 minutes, the GA will solve in 26 minutes. Groovy can solve more than 12 hours, but the quantum computing can solve in 6 seconds. Very fast, 6 seconds. And the GA and Groovy we run is already in high HPC. It's already around HPC. It has more than 30 CPUs already. Yeah. So it's already very fast HPC, but using quantum is very fast. So this case actually gave us some confidence that we can use quantum computing to solve the building control problem. And in this conference, my postdoc Zhipen also presented a paper. We test this into building to grid integration problem. So we look at a cluster of buildings, look at 31 commercial buildings, and how we control them together. So using the quantum computing, a typical building to grid integration problem. And this is the result. So we use 3 days simulation. The MATLAB solve in 18 minutes, but quantum can solve in 10 seconds. For this problem. So basically, if we look at think about in the urban scale, we have thousands, tens, thousands, millions control variables. You cannot use a traditional way to solve it. You have to find a good other way to do it. So quantum computing is very good for a large scale mixed integer programming problem. Yeah, in conclusion, the machine learning-based approach control provide a promising approach potential to advanced building controls, as you can tell, right, at a small scale. And the performance varies at different machine learning approaches because the nature of the reinforced learning and the DPC and DPC. And also QC, quantum computing, provides an alternative way for a fast, larger scale, real-time control for future building cities. That's it. Thank you.
Okay, thank you very much, Professor Dong. I think this is the first time I hear about the quantum computation used in the building simulation and control. Very interesting. So once again, we try to take one question from audience. Yeah. So we choose the first, sorry.
Thank you very much for this very interesting presentation. It's very insightful. I have a question about the mixture that you have done between neural networks and the physical equations. So in some cases, the physical equations, we have a well-known knowledge about all the constants and the variables that we can include. But in some applications, constants are very difficult to know. So my question is, maybe in controls, this is not a big problem. I'm not an expert in this domain, but for example, in indoor air quality, which is my expertise, we find it difficult to know some coupling between some pollutants and the materials. So sometimes we just give values for constants and we give them in the physical equations. My question is, do you think using those values, which we just estimate or predict, has a very misleading effect on the final solutions, or it can be still controlled and the machine can still predict, or I don't know, maybe how drastic is the effect of we don't master all the information? Thank you.
Yeah, that's a very good question, especially for indoor air quality. So, refer to the specific equation, race weather equation. There's a lot of assumption for people's pollutant generation rate, right? So from each person, or each person is different. So what do we actually incorporate that equation into our control strategy? So we found, so the only way to make sure it is working is through validation. So we have a small test bed, actually give it a control signal and give it a lot of measurement. So we just verify actually, what we expected from simulation is true in the real measurement. I think that's the only way you can verify that your assumption is correct. You cannot use any. A lot of people put like alpha, beta parameters before it, try to calibrate the model, but that's not really a good way. It's a good way to use measurement to verify it. Yeah, thank you.
Okay, let's go to the third invited speaker. And the third speaker from Zhejiang University, and Professor Gang Tan. His topic is a regulation of solar and LWIR for Windows, material simulation and application. So let's invite. So now let's give time to Professor Tan.
Good morning, everyone. Thank you, Professor Gao, for introduction. And I just learned a lot from Professor Dong's speech. And my talk is about some new materials, and then talk about simulations, some tools or methods we use to quantify the energy savings or the effects of when we apply the materials to the buildings. First, Today, my talk will focus on the windows, because windows, we have the visual certification for the occupants, and also because of the windows, we have the glasses. So a lot of solar energy will enter the window, the glass, and heat the space. Therefore, we have some methods or mechanisms to control the solar heat gains for the space. Therefore, we have the research area, we call it smart windows. There are a lot of researches about smart windows, and also there are a lot of materials we can use to control the amount of the solar and also the spectrum of the solar enters the building. There are two examples I give here that including the electrochromic smart window. This one, the material will be triggered by the electro signals and all the voltage that will charge the material, drives the electrons move from one side towards another side, and then changes the color or the optical properties of the material. And here, give one example, we can see that we have the 1 volts, then the material still quite bright and clear. And when we increase the voltage and reverse the voltage, we will see that materials optical actually property changed from the light color to the dark color. And with the dark color, we can see that is optical properties that from the 400 nanometers to the 2000 nanometers. That's the solar part. We know that, and we can see that the change, the block, the operation mechanism for this electrochromic smart windows will be controlled for the total solar part from the visual part, which includes 318 nanometers to the 760 nanometers. That visual part reduced, transmission reduced, and also the NIR, the near infrared part enters the glass, also reduced. So this one we call it as a combined or simultaneous visual and NIR control for the smart window. So this is the electrochromic smart window. And another one example is the thermochromic smart window, which is controlled by the temperature of the material. For example, here give two examples of the thermochromic materials. One is VO2, which is transferred between the insulator and the metal phase because of the temperature. We know that the VO2 nanoparticles, the phase transition temperature generally at 68 degrees C. But for our building application, this temperature is too high. Therefore, we generally use the tungsten doped the nanoparticles of the VO2. With the doped nanoparticles, we can reduce the phase transition temperature from the 68 degrees C to, I remember the lowest about 26, 25 degrees C. So that is suitable for our building applications. We can see that is a red color, the solid line and the dashed line. And for the VO2 nanoparticles, that it mainly controls the near infrared radiation entering the glass or transmitted through the glass. And for the visual part, it doesn't impact the, doesn't change the transmittance with the temperature, okay? But for the hydrogel that itself mainly control very limited for the visual part, and that's the dark, the solid black one, and the let me say the solid black dashed line. We can see that it controls mainly for the visual part, but for the near infrared part, the control is limited. If we combine these two, that becomes the blue solid line and the blue dashed line. So we obtain the combined effects for the visual part and the near infrared radiation for the solar regulations for the window. That's mainly for the traditional smart windows. As for the unconventional smart windows, we have the humidity triggered smart windows. For example, here we have one that is calcium chloride. This salt, what kind of salt, will be confined in the microstructure of the silica and the titanium matrix. So this material could be triggered by the humidity change, and the phase will transfer from the solid to the solution. The solid will have the scattering effect and becomes that block a lot of the solar energy. But when the humidity increase, the salt will absorb the water humidity from the air, and then becomes a solution, and then becomes the transparent. So that's the working mechanism of the this kind of smart windows. And also we have the mechanochromic smart windows. So we have that kind of material have the microstructures. Microstructures, we control the microstructures scale. For example, if we want to block which kind of the or which segment of the the solar part of the radiation, and then we control the scale of the microstructure will be similar as the wavelength of the solar radiation. Then we will block that part of the solar radiation. And with the stress, we reduce the microstructure. Then we will remove that part of the blocking effect. And also we have the magnetochromic smart windows. This we move the nanoparticles and then changes the optical property of the structure. Okay, so that's our. There are three examples of the conventional, unconventional smart windows. Now, I would like to introduce a little bit more details about some examples of the thermochromic materials. This we synthesized some we call it the hydrogel that PAM. This is the hydrogel, but we modified the length of the molecule of this hydrogel. So in the last slide, we showed that the hydrogel will not control directly to the NIR part, but with our modification, we will see that is with the length increase, we will observe the control or regulation to our near infrared part of the solar radiation. So we can see that this hydrogel, we have the phase separation from the hydrophilicity and the hydrophobicity. That is the swallow or the collapse state. So the swallow state is that when the temperature, the hydrogel temperature lower than the lower critical solution temperature, then it the molecule is quite how to say flat and then well uniformly distributed in the water. So it would not block our solar radiation. When the temperature increase pass through, for example, for our material, the phase transition temperature is 31 degrees C. We know that we use water. Water absorbs part of the solar energy. So the temperature increase above this is normally observed. And then the molecule will collapse. Then the size of the molecule becomes that similar to the solar radiation's light wavelengths. Therefore, it blocks our solar radiation. And so we can see the picture that the first one is transparent and the right one is translucent and block a lot of the solar radiation. And in order to quantify this kind of hydrogel smart windows energy saving, and we use these 4 types of the glass substrates, including that two glasses we used it to simulate the double pane windows, okay? Or we compare with the low E glass. So we use ITO as the low E layer. And also we have the CMO. So these 4 substrates either incorporated with the hydrogel or without hydrogel. And we can see that is a metal coating layer. We used it for the interior side. The interior side, we have done some of the simulations. We found out that for the buildings, the interior side of the surface, the low E effect always benefits the energy savings. So that's why we use the interior side of the windows with the low E coating to compare the energy savings. So here we tested the optical properties. We can see that with different thickness of the hydrogel, the blocking effect to the VO part to the near infrared part has different effects. And also we compared our samples with our physical limit line for the hydrogel the performance, and we can see the blue line. There we have one close to our limit, so the result is pretty good. And we obtained the maximal, so total solar regulation is about 35.5%, but we can maintain a good transparent or luminance for the 88% when the temperature lower than our local lower critical solution temperature. So it's very clear our sample, and we obtain a good luminance regulation with the temperature above that critical solution temperature. Using Energy Plus, we created models to model all commercial building, use our 4 type of the smart hydrogel embedded windows. We observed that is a major effect or the benefit using this hydrogel windows less at the peak CV. Mainly at his summer, okay? And we can see below we obtain the significant energy savings from the 30% for the Tucson, and also but for Los Angeles, the savings about 10%. Depends on the ambient temperature and the solar radiation. So that's the hydrogel, the thermochromic smart window. We give one example. That's for the thermochromic windows, the hydrogel actually it reduce our visual comfort for the occupants. Instead, whether there is a way for us to maintain a good visual level, but we can still control the modification and the near infrared part of the solar entering our building. For the summer, we don't want the NIR, the near infrared part of the energy entering our building. But in winter, we want that is heat enters our building. And another important thing is that for our long wavelengths infrared radiation, that's about 2.5 microns to 25 microns. For that part, we want in the summer, we get the high emissivity property. And in winter, we get the low E property. Then we can keep the heat within our space. But it's very difficult for us to modify or regulate our long wavelength infrared and still maintain a good or an acceptable visual luminance level. Therefore, we constructed micro nano level of the structure. We call this fabric parrot structure. So we have that is a top layer is VO2 or nanoparticle embedded into a polymer. And then we have a PMMA layer. This PMMA layer, we call it is a fabric parrot space. Under that, we have a low E coating. So the top layers of VO2 and the polymer compared to the low E layer, these two have very different refractive index. With the osmotic refractive index, and between them there is a PMMA spacer. Then we constructed we call it as a parrot structure. This structure will enhance our long wavelength, the infrared part of the absorption. Actually, absorption, we know that gray body that is absorption or absorptivity equal to our emissivity. So if we enhance our absorptivity, then our emissivity actually simultaneously enhanced. So that we obtain that structure, and then we combine into the interior side, the low E coating, we obtain that special optical property that for our long wavelengths, the 2.5 to 25 microns, we obtain the winter, we got the low emissivity. And in summer, we get the higher emissivity. But we still maintain some limited regulation, dynamic regulation for the IR part. So this method, we obtained that as the right side, we listed the result. Of course, we can say that is the regulation, the effect is the range is still limited. We hope we can improve the material system. We will optimize different, we choose the better material system to achieve better regulation for the sonar and the long wavelength infrared part. And for the simulation part, we conducted some sensitivity analysis to see that for the exterior side of the windows, the emissivity will be higher or will be lower, will be preferred for the energy savings. We found out that for the cooling, the solar part is smaller, transmittance is smaller, and the long wavelength infrared is higher than the best. But for the heating condition, reversed, okay? And also we use the energy plus to conduct the energy savings and found out that this kind of the material, we call it is weather self-adaptive material. And it can or somehow suitable, applicable for the different locations of the weathers. And we found that for all the climate zones, the energy savings or our window structure outperform than the regular low E windows, okay? But here that we observed that for the long wavelength part, even for this material, we found out the optical property actually is flat for the entire long wavelength infrared part. Therefore, because we call this kind of material is a broadband material, therefore we can use the traditional calculation method in the energy plus, integrated in the energy plus to quantify its performance. But for some optical spectrum selective materials, we may not be able to directly use the average emissivity that used in the energy plus calculations. There is another method. We use the power generation combined with the solar regulation. So this one that I directly jump to our structures. We can see that our structures, we have the outer layer is a PET. This kind of this polymer is very weather durable. Okay, and also solar part, the light transmittance is very high. Okay, and then we constructed the power generation, or we call it as a solar cell. This is perovskite, this material, and we have the silver nanowires, and the other part are the electrode is the ITO. But in the middle, we use the VO2 nanoparticles. These VO2 nanoparticles not only worked as the phase transition material, but also bridge or place good band alignment with perovskite and ITO. We can see that is an energy level diagram. That is just like we step the stairs. We can see that is perovskite and the ITO. We added the VO2 into it. We added another or additional stair. Then we make this energy efficiency, the power conversion efficiency becomes a different way. We can see that generally the solar cells temperature increase, then the efficiency will decrease, right? But for our structure, that is a PCE at 45 degrees C, the efficiency is higher at 25 degrees C. So we get the double or two-sided benefits using this structure that we got the energy savings from the HVAC. We can see that use our structure compare without the VO2 in the middle layer, our HVAC energy we get the higher savings because we have the solar regulations. And for the solar power generation, we got an additional energy benefit because we generate more energy. So we get more energy benefit from this special structure design. Okay. Once again, we can see that our optical spectrum for this structure for the long wavelength infrared part still flat. So that's still for this structure, it is broadband material. Okay. We can use energy plus to quantify that. But there are some of the materials, they are the spectrum selective. For example, the hot topic right now in the research area, that's daytime radiative cooling. Daytime radiative cooling, we use the separate control for the solar part and the long wavelength infrared part. The solar part we want is a very high reflective property for this material. So this material would not absorb only solar energy. In addition, we will construct the material has the property for the emissivity. We call it during the range of the 8 to 13 microns. This range we call it atmospheric window. The infrared radiation can transmit through our atmosphere to the outer space. The outer space always has a very low temperature at 270 degrees C below zero. Then we will obtain that under the direct sunlight, our surface temperature could reach below the ambient temperature. So this is the working mechanism of the daytime radiative cooling. This one we can say that we only have high emissivity at the atmospheric window. So this kind of we call it a spectrum selective material. For the this kind of material, we will use the integral calculation for the power. For this part, that Professor Yan Da from Tsinghua University have incorporated the calculations into the whole building energy simulation test software. So we face this difficulties that because the basic heat equation of the state space model is linear functions. For this band, the spectrum integral calculations, we cannot directly treat them in the calculations. Therefore, in the test, in the test, Professor Yan, they built a standalone module to treat the spectrum selective material and to calculate that is the power. We can say that is a radiation of the power from our radiative cooling material surface. Okay. So the data, how to say, exchange with the software, and then solved the problem that found out the difference and the error is quite small. So this method is acceptable compared to that we purely use the integral calculations. That's one method, uses full spectrum integral calculations. Another method that some people to try to use that, we simplify them. And because the atmospheric window is just for the 8 to 13 microns. And before that range and after that range, we just separated the entire non-wavelength infrared into 3 parts. And then introduce some regression calculations to some of the coefficients, and then to quantify the different spectrum selective materials, and then use these coefficients built into our energy class or test the software, and then we call those coefficients to do the regular calculations, treat them as the 3 segments, the broad band materials. This also can work pretty well. And we can see that these coefficients and have a very good linear relationship with the temperature. Okay, therefore we can directly linearize the calculations, and the verification shows the difference compared with the full spectral calculation. Integral calculation is acceptable. Okay, is small, and here that I just. This is not a peer-reviewed work. This is just the internal calculations. And there is an error that is we switched the results for the ideal broadband material and the ideal spectral selective material. Finally, here we just one example for the applications of the spectral selective material. So first is that we build the water box. And on the top of the box, we have one layer of the radiative cooling material or film. And we use just directly the analytical model. Just we calculate the integral the sky or the radiative cooling power, and compare with this controlled water box experiments. And found that his analytical calculation also gives a very good agreement compared with the experimental measurements. And also build some reduced scales model houses and measured the surface temperature and also the indoor air temperature. And we calculated using the analytical model and found out the result agreed pretty well too. And here give some example shows that is experimental tests for the performance of the radiative cooling material used for this reduced scale model houses. We can see that is the surface temperature and the indoor air temperature pretty good. Pretty good is a significant difference compared with the metal houses without applied with the radiative cooling films. And also measured the total radiative cooling power for the different sides of the orientation of the building envelope, and get is cooling power for the different walls or the roofs. Just 1 minute, I want to take this chance to introduce my lab that we developed built in the center of Yangtze River Delta, Jiashan, Zhejiang province, and that's also belongs to Zhejiang University. And our research topics covers these four: the light thermal, light electric, wearable electronic fabric. And thank you very much.
Thank you, Professor Tang. And due to the time, we run almost 20 minutes late. So also one question, please.
I'm very interested in the map of world map to show the energy saving potential. Would you like to show it again? PowerPoint. Yeah, the back. Why North Canada, Russia, and Africa and Australia? I think it looks their energy saving potential is higher than China, Europe, and America.
Yes, this also because of this is the net energy savings, and we didn't use the normalized, and also because of the solar radiation and also the heating. This will also have the heating energy savings, not only just the cooling, because this we call it is the weather adaptive and dynamic regulated, because in the winter we will let more energy come in, and in the summer we reduce the energy coming in. Depends on the baseline.
Okay.
Yeah.
Thank you.
Okay.
Thank you.
Thank you. Wait a moment. So sorry for the late. Okay, so we have the first speaker, and from Polytechnic editorial, Professor Corredo, and his topic is detailed simulation vs standardized method in energy performance assessment of buildings in a legal context. Yeah, let's give the time to the Professor Corredo.
Thank you. Thank you. Good morning, ladies and gentlemen. The topic of detailed simulation versus standardized methods is a hot topic in Europe and also out of Europe. A general question is whether it is better to perform, to make simulations with very detailed tools, or maybe with very simple tools. The question is very simple, but the answer is not simple. As I will show you, there is not a univoc answer. And in my presentation, I will try to address this topic. My presentation is basically split into two parts. In the first part, I will give an outline of principles relevant to the EP assessment, energy performance assessment of buildings in a legal context. In the second part, I will give an overview of the most recent international standards, the so-called EPB, Energy Performance in Building Standards, mainly developed within ISO, International Standardization Organizations, and SEN, the European Standardization Organization. Starting with the first part, I must say that in the European Union Energy Union strategy, a general objective is to ensure Europe's energy supply to be safe, viable, and accessible to all through wise energy use and effective measures to fight climate change. But a more specific goal is to improve the energy performance of buildings by increasing the energy efficiency and enhancing the use of renewable energies in both new and existing buildings, indoor climate requirements, and cost effectiveness. So an important aim is to develop new tools for these two specific goals that represent what I mean by legal framework. So to calculate the performance with the aim of checking, verifying the minimum requirements on the energy performance, both for new buildings and for existing buildings, subject to major innovations. And on the second part is about the energy performance certifications of buildings. As regards the general requirements of an energy performance assessment, to facilitate the comparison of best practice and support the internal market for construction products, an energy performance assessment should comply with some requirements. First of all, to be accessible, transparent, and active, and also taking into account different types of energy services. The European legislation addresses a number of compulsory energy services to be taken into account, such as heating, lighting, cooling, air conditioning, ventilations, and so on. But also take into account specific aspects related to outdoor climate and local conditions. In the last 20 years, a very huge activity has been performed mainly through a joint work of ISO and SEN to develop a comprehensive package of technical reports and standards. Today, we have more than 50 standards. Maybe they are too many, maybe some thousands of pages, but that's what we have now. And so that's what we have to use, and more especially practitioners and engineers, architects are more and more using these standards in their activity. So the model, the method is mainly based on physical models and forward models. So on one side, you have the system structure and parameters properties and the forcing variables. And on the other side, the main output variable is the energy use of the building. If we look at the requirements of an energy performance assessment model, we see that at least 6 or 7 different requirements should apply. First of all, a model should be accurate. It means that the deviation between the assessment results and reality, assuming the same internal and external condition, building use and operation, should be as low as possible. But also the robustness is an important requirement, defined as the ability to handle a wide variety of situations without a significant loss of accuracy. But at the same time, the flexibility, which is the ability to cope with non-standard input data, the transparency, which is the clarity in definitions of variables, parameters, equations, and system boundaries, the reproducibility, which means the limited deviations of results obtained by different experts using the assessment method and same building, and the legal security, which is meant as the accordance with the directives and national regional regulations. This is about the assessment models, but also it's not all. Also, the input data should comply with some requirements that include the accuracy, it is the deviation between the input datum value and its real value, the unambiguity, which has to do with the clearness in definition, units and symbols, the distinction, which is the quality of having a visible effect on the assessment of the energy performance, the measurability, quality of being measurable, verifiability, the enforceability, which is an easiness of slowness in deteriorating, for example, due to a short lifetime or bad maintenance, and the simplicity, easiness to understand and easiness to assess. In Italy, in a conference more or less 10 years ago, it was asked to several practitioners to develop an energy performance assessment on the same building, and they were supplied with the drawings, every kind of information. Well, at the end, the result was completely variable from one practitioner to the other, even using the same software. So you can understand that it can be a problem. There is also a loss of accuracy in the AP assessment due to several causes. One is any simplification in mathematical modeling. It means simplifications in modeling of physical phenomena, for example, due to discretization, spatial distributions uniformity, and other assumptions, but also in the neglecting some physical phenomena that are considered unimportant. Another possible cause of loss of accuracy is related to the simplifications in the specifications of input data. In standards, sometimes it's asked to use, or it is allowed to use default or approximate data to characterize individual components, or in other cases, use of a lump sum approach to characterize a group of components. Also, the ambiguity in interpretation of input data can cause a loss of accuracy in cases in which multiple choices are allowed, or maybe qualitative data. Typical case is inertia is low, medium, high. What does it mean? It's not clear. Missing information. And finally, uncertainties regarding input data, both about the parameters and properties that characterize the system and about the boundary conditions. I would like to give you a couple of examples. This is a typical applications of a Monte Carlo method in which you have a tool that performs the energy building simulation. You define probability density for different input data, and you apply the Monte Carlo method to define the output, the energy use of a building, which is not anymore a deterministic output, but it is described by a probability function. Now it is the results of such a kind of application in which the blue curve takes into account the uncertainties in the physical characteristics of the building and of technical building systems. But the red line also takes into account any uncertainty in user data, in climate data, and so on. So the result is that if the data are poor quality, the consumption, the real energy use could be very spread over a very, let's say, large and spread probability function. And the result could be that any kind of energy performance classification would be meaningless. You see, that building could be in class A or in class G as regards the real consumptions before of the uncertainties and simplifications in the model. So a conclusion is that it is always recommendable to integrate the energy performance assessment with a confidence interval estimation. I guess that in the future, the final output of an energy performance assessment will not be one number, but a confidence interval. Here is another example regarding the determination of thermal characteristics of an existing wall. You have different possible approaches, at least 6 according to European standards. And you see that each approach can be classified according to the detail of knowledge of the building, of the component of the wall, for example, and the accuracy of determination of the due value. For example, in the A, you do a core drilling, it's not very common, of course, and you make a direct measure of material characteristics, you get a high level of accuracy and of detail. But in case E, for example, you measure the U value by the heat flow meter method. You have a good level of accuracy in determinations of the U value, but you don't have the detail of the layers of the wall. So it's really important to be aware about how do you manage the input data and what's the results in terms of detail and accuracy. So to complete the first part of my presentation, I present this triangle that represents, according to my opinion, the three most important requirements of an EP assessment in a legal context. On one side, the accuracy, of course, is the most important, which is related both to model robustness and flexibility, and also to the accuracy of input data. On the other way, the simplicity is important as well, and it is more related to the simplicity of input data, but also to the user-friendliness of software tools. The third aspect is the reproducibility, which is related to model transparency and unambiguity of input-output data. As you can see, there is an inconsistency of some of these requirements. So it is necessary to find the best trade-off between different requirements. In some cases, a simple method is better. In some other cases, a more accurate and detailed method would prefer better. Moving now to the second part of my presentation, I will give you an overview of the most recent international standards. First of all, I must say that ISO and SEN standards follow a so-called holistic approach. So trying to integrate and aggregate all elements and energy services. It is represented by this triangle that represents the globality of all ISO and SEN standards. Some of them are more related to defined boundary conditions or competent input data. Some of them are more related to the final calculations of the energy performance of the building. Several technical committees, both in SEN and ISO, were involved. Most of them worked jointly. Of course, I'm not going to bother you with all the technical committees, but just to say that it has been in the last 20 years a very huge activity, a very intense activity. Mainly, the international standards are based on three different steps. Starting from the end, the overall assessment of the energy performance is addressed in the so-called overarching standard, the EN ISO 52000. But before that, there is a step number 2 in which the energy balance of the building, of technical building systems, is solved. And before that, the step number 1 is the assessment of thermal energy need, considering fabric and developed elements without technical building systems. As regards the overall energy performance assessment, the most important issue is how to define the assessment boundary of the building, which is the boundary where energy can be either imported or exported. It's not easy to define this boundary. In some cases, some of the energy flows that cross the boundary are based on the meters, for example, gas, electricity, district heating. But for active solar, wind, or water energy systems, the assessment boundary is the output of the solar panels, the output of solar collectors, or of the electrical generation devices. As regards any kind of transformations happening out of the assessment boundary, it is taken into account through primary energy factors. In the determinations of primary energy factors, it is recommended to distinguish between any kind of transformations happening on site or off-site, and off-site is distinguished into nearby and distant. So 3 different perimeters are defined. Then, as regards the fabric, the building as such, the building is partitioned into thermal zones for the purpose of calculating loads and needs. And the technical standards define a new criteria for splitting, for partitioning the building, based on definitions of thermal zones and service areas. A thermal zone is aimed at calculating the heating and cooling load, but service area are more related to the analysis of different technical building systems related to different energy services. Different approaches, of course, are possible. The general distinction is between detailed and simplified. And according to standards, the detailed approach is more similar to the approach used in common simulation programs called like Energy Plus, in which the interaction between the building, the thermal zones, and the technical building systems is taken into account during the simulation, during the calculation. While in the simplified approach, in the first step, the thermal energy need for heating and cooling is calculated regardless the kind of technical building systems, only considering the passive part of the building. And after that, there is another part of calculation in which the heating system, cooling systems, domestic hot water, and so on are taken into account in the simulator. Any interaction between the passive part and the active systems is taken into account in a simplified way through some efficiencies or the so-called recovered and non-recovered heat losses of different components. As regards the determinations of heating and cooling loads and thermal energy need for heating and cooling, the international standards allow 3 possible approaches. The first one is addressed in the ISO 52070 part 1, and it addresses a detailed full dynamic simulation in which no simplifications are imposed and only general assumptions, boundary conditions, and equations are provided. It is the typical approach used in research activity. When we use Transys or Energy Plus or any other kind of software, we use that kind of approach. The other 2 methods addressed are the simplified hourly method, in which internal air heat balance is solved on an hourly basis. And each construction element is modeled separately through a few Lampert parameters, but of course, many simplifications are applied. While the monthly method that is still applied in Italy and many other countries for legal applications, it's only fit for energy need assessment. It's not able to calculate, of course, hourly values of the cooling loads and the temperature. And correlation factors are used in the balance of a zone on a monthly basis. As regards the input data, the simplified hourly method uses hourly meteorological data, while the monthly method, of course, monthly average meteorological data. And the same is for schedules for occupancy, appliances, lighting, ventilation, hourly schedules on the left side versus monthly average values for the monthly method. The simplified hourly method is based on Lampert parameters for storage effects, while the monthly method uses correlation factors to account for dynamic effects. Well, if we compare in a few words simplified hourly method and detailed simulation, a simplified hourly method has several simplifying assumptions, specific conditions, and standard values, while a detailed simulation can reach a high level of detail with several assumptions in terms of temperature uniformity, flow dimensions, mass distributions, and all other aspects that can be considered in a simulation. In this and in the following slides, I try to summarize the main advantages and disadvantages of the 3 approaches according to international standards. The main advantage of the simplified hourly method is that the amount of input data is comparable to that of the monthly method. So it is a limited amount of data. The main disadvantage is that it is not a suitable reference method in cases where specific complex details are involved. For example, thermal interaction between zones. I will show you some issues related to this method. The monthly method is really very simple, easy to follow. So in terms of transparency, it is, of course, the best choice. And it can be easily tested in terms of reproducibility and verification. But it cannot take into account the influence of time variation in weather and operations. And it cannot take into account the dynamic interaction in a transparent way. A detailed fluid dynamic method takes into account non-linear properties in the energy modeling of the building and its technical systems. It allows to model advanced technology and building automation control systems. But as regards the disadvantages, it introduces a lot of choices, details, and complexities. So this is the reason for which it is quite difficult to be used in the context of building regulations. For the lack of reproducibility and transparency. It is one of the three elements of the triangle that I presented before. Some critical issues related to the applications of the EPB standards are presented in this slide. In terms of overall EP assessment, and a main issue is how to define the assessment boundary. I mean, there is a problem of discrepancy of in the definition between different countries, between different contexts. So the result is that it's sometimes difficult to compare results. Also, primary energy factors, how to account export energy as an important effect. In a recent European standards, we tried to compare the energy performances in typical building stocks in different European countries. It was not possible because if we use the primary energy, each country had its own primary energy factors completely different from the other. So it was not possible to make that comparison in a correct way. Another issue is related to the energy balance of the building and of technical building systems as regards, particularly as regards the effect of building automation and control systems, especially in smart buildings. It's really complicated. It's impossible to use the monthly method, but even the simplified hourly method is not able to catch every possible function of a building automation and control systems. Finally, also the assessment of the thermal energy need in terms of choice of the calculation building versus building category type of assessment is really challenging sometimes. And also modeling of adaptive building envelope elements is quite challenging. By the way, a new standards has been developed just this year, will be published regarding how to use the adaptive building envelope elements and to integrate them into the calculation with the simplified hourly method. So to finish, I don't give an answer to my first question. It is an open question. Are the PB standards the best response to the requirements I mentioned before? I'm not able to give an unique answer. It is difficult to answer because it depends on several items. It depends on the building size and complexity, of course. It depends on use category. For example, residential buildings are completely different from commercial buildings. It depends on climatic conditions. Some simplified methods for heating work well in the Northern Europe, but if we apply them in the Southern Italy, it's impossible because we have very high solar gains, and it causes an overlap between gains and heat transfer profile that makes it impossible to use such kinds of methods. It depends on type of application. It concludes my presentations, and thank you very much for your attention.
Thank you, Professor. So once again, we try to take one question from the audience.
Thank you very much for the presentation. We will move forward in Europe from using energy use intensity to emissions or greenhouse gas emissions as an indicator in the EU, and we have to revise all the member states' regulation and only communicate in carbon. In this regard, are we going to just use the same standards like the 52,001, for example, and then add the conversion factors, or would it be more logic to change also the calculation method and instead of reporting energy, report emissions? What is your take on that? Where should we go?
Yeah, I must say that the ISO, the overarching standard, the ISO 52000, is a very, let's say, flexible standards. It is already ready to be used to calculate not primary energy, but other kinds of, using other kind of metrics. Then it's a matter of defining the numbers, the values. Because if you apply that standard today, it's not compulsory to calculate the primary energy. You can, let's say, starting from delivered and export energies, that's the final output of the calculation. You can apply different factors to calculate the carbon emission instead of primary energy. It's a choice, a national choice. Some country already chose that kind of approach. And you can use that standards without any problem. Moreover, there are some common parts in the standard, but also some national choices that are free. As you probably know, there are some national annexes that can have the same structure, but in each country it can be decided to use different metrics and different parameters to take into account local conditions as regards climate and social aspects and whatever.
So until now, we finished all the invited talks in this section. And thank you very much for all of you attend the section until the last minute. And now, please, we finish all the talks and please enjoy your lunch. Thank you very much.
好了，这